Hello and welcome to my series of videos on redox chemistry. Sorry, let me just write down this title. Now you're probably wondering why I've written redox in red and yellow. So the term redox actually splits off into two larger words. The red side of redox actually means reduction, and the yellow means oxidation. So you're probably asking yourself, it's like reduction, oxidation, what do these terms mean? I'll get to that in the next slide. So imagine that we have, say, two regions, and I'm going to represent these by circles. And I'm actually going to name each circle inside, hopefully, as species 1 and species 2. Hope everyone can read my writing. So what redox chemistry is actually talking about is an electronic transfer between both of these circles, or these species. So a species in chemistry can represent, say, an element, it can represent an ion, it can represent a molecule, it can represent any sort of chemical entity. So what's actually happening between the yellow circle on the left and the red circle on the right is that we've got an electronic transfer. So if I just draw an arrow, so an electronic transfer from species 1 to species 2. So we can say that if electronic transfer is occurring from species 1, we can say that it is actually losing electrons. And the red side is actually gaining electrons. So if I just move this picture up here, that's not working very well. Okay. The terminology of losing electrons is actually oxidation in this case. And the term of gaining electrons is actually called reduction. So I'm going to try and keep these colors consistent. Now, if I go on to the next slide, alright, so here I'm going to add in a picture of a famous chemist. And this chemist's name is Antoine de Lavoisier. So let's just spell this. Hopefully I spelled this right. So he was a French chemist, and he was considered a father of modern chemistry. Now this was in the 18th century where he lived. And he actually came up with the terminology of reduction and oxidation. And he was experimenting on metal ore to try and get the metal that he required out of that ore. And he found out that if you reduce down the ore to the required metal, you're actually losing oxygen. But conversely, you are actually gaining hydrogen gas. So, when all these terms were made centuries ago, we've never actually changed the terminology of oxidation and reduction, because it seems quite nonsensical that reduction actually means the gain of electrons. And from my past experience, I know that a couple of my students have actually found it quite difficult to actually realize that reduction actually means the gain of electrons. But it's important to note that when these terms were actually founded upon, they weren't actually looking at the transfer of electrons. They were actually looking at the loss and gain of primarily oxygen gas. And then they found out that hydrogen was also contributing towards the electronic transfer, because you can actually make hydrogen gas out of 2 protons and 2 electrons. So conversely, you can actually have oxidation, and similarly to reduction, this means the gain of oxygen, or the loss of hydrogen gas. So that kind of makes sense, because if you have, say, iron and iron metal and you leave it out into the environment ungalvanized, over time it's actually going to react with the air and actually rust. It's going to form iron oxide on the surface. So yeah, let's continue on.